about me. I am a Java senior developer at IBM, and I have several years of experiences with, for example, embedded systems like Arduino or Embed or Nordic. Then also several years of experiences with Java frameworks. Currently, they are already a little bit obsolete, and also experiences with SQL and NoSQL databases, as well as with cloud solutions. But nevertheless, what I am patient hacker. During my spare time, I build things. I have several ongoing projects which are in progress. For example, weather station, CNC, then reflow oven or Bluetooth low energy connected model train. And this is also a very good opportunity for me to learn something new. So at the beginning, IoT current state, Internet of Things is a rapidly growing market and technology area based on IDC prediction. In 2020, this market will be $7.1 trillion value, and it will have 10 to 100 billion of IoT devices. So where all this money will go? Primarily into these IoT-enabled devices, but these devices will produce a big amount of data, so also infrastructure must be enriched to be able to cover this big data flow, and also cloud services, because IoT will be nothing if this data will not be processed and analyzed back then. So this is also a very good opportunity for technology leaders to introduce some standards for IoT communication, because this is not yet specified. And IoT systems has variable scales. For example, home automation, it generates very few messages per minute. Through enterprise automation, where you have regularly several messages per second, through M2M and SCADA automations, where you have, for example, 3,000 messages per second. So these systems must be also scalable. First, before I will go into topic, I'd like to tell a little bit story behind this. So me and my colleagues, we were also hackers, and we still build some things, and it turns out that we are facing similar problems. We have usually sensors, some microcontroller connected into this sensor, and we want to provide this data into cloud. But these systems are very weak. It's not able to handle TCP stack or UDP stack, so you cannot send any message to outer world. Therefore, we think, what if we put some device in between, which will be able already communicate with network, and we make this thing, this software, modulable, so you can reuse several modules which you want to use in your solution. For example, connection with serial port and so on. So, and this is the beginning of IotaGate. IotaGate is not IBM product, but it is a product from developers for developers. It improves network performance because you can create filters, and decrease implementation cost, because I already said you can reuse modules which are already prepared. Easy to deploy on most common ARM platforms. So you have, for example, embedded computer like here, Raspberry Pi, and on this Raspberry Pi it's running Linux and Java 8, and our IotaGate uses this Java 8. So basically every ARM computer which is able to run Java 8, there can be deployed IotaGate. And it can also support IBM products, but not just IBM products. Basically, it can support any kind of products. And when we have these modules which can be built into IotaGate, this is very good time and cost reduction. So here we have a high-level solution. of IoT network. So at the left side, we have some sensors and actuators. These are connected into IotaGate, for example, with wired or wireless protocols. From wired, there are many of them, for example, SPI, I2C, one wire, or serial port. From wireless, you have Wi-Fi, Zigbee, Bluetooth, Bluetooth Low Energy, Gazelle. So there are many of them. And it goes into IotaGate. IotaGate can process this information later on and create MQTT messages. These messages are then sent to broker. And if some external server is subscribed on this specific topic, it will receive notification. And this external server then can store this information or do some additional processing, provide a RESTfull API, make Android notification, and so on. So there are a lot of possibilities here. So as you can see, IotaGate should be as closest to sensor as possible. This was also our target. So we try to target it embedded systems. And because these embedded systems has very small resources, for example, not very big RAM, and also storage is limited, we try to have as small footprint as possible. And to achieve high data throughput and high performance, we use fork join. This is already introduced in Java 7, but in Java 8 it was greatly improved. And so we are able to utilize all cores in ARM processor, because these embedded systems usually have more than one core, except my old Raspberry Pi, which has only one. So in addition, it will be nice to have a highly configurable application, but if this configuration will be like writing something into file and then store and restart application, it will be quite boring and difficult for end user and beginners in IotaGate to make application working from beginning. Therefore, we decide to also build into IotaGate some configuration UI. This is served by Jetty. And simply you can drag and drop your components. If you are familiar with Node-RED, who already did something with Node-RED? Obviously, nobody. Nice. So if you are familiar with Node-RED, then you will be also familiar with our UI, because we were highly inspired with this. And this UI is then detachable, so you can have a headful or headless application. Once you configure it, and if you are fine with this, if you want to even reduce your memory consumption, you restart your application into headless mode, and then Jetty will not start. But what is most important in IotaGate is modularity. We don't want to build system which is able to cover all possible protocols and all possible ARM embedded devices which can be created. But we try to force people to create modules. So when you, for example, want to use serial communication for BeagleBone Black, you just use a serial communication module which is specifically created for BeagleBone Black. This is also, maybe sometimes it's downside, but sometimes it's advantage. Downside, this means there must be some kind of module, or you have to code it by yourself. But advantage is you are also cooperating with hardware closely, and therefore you have a higher performance. So I mentioned our UI, so this is how our UI looks like. At the left side, we have a list of modules which you can place into your worksheet. So this list of modules is divided into input and output modules. In the center, you have worksheet with one flow which is configured this way. So we have a serial input module, which is then connected into two mixed modules. Mixed means it has input and output functionality. And from mixed modules, it goes into output modules. Input module from our perspective is producer because it produces some messages into our system, and output modules are consumers. What is also interesting here, you can have many-to-many relationship between these modules. And everything here we called flow, and you can have as many flows as you want. And chain between these modules is connection between. So let's go a little bit into architecture of our application. So this is web UI, which can be then detached if you don't need it anymore. And this is a Java 8 based application. At the beginning, we have a gateway service, which is basically starting point of our application. This gateway service then runs Jetty. And Jetty basically starts two servlets, one for providing static content. This static content is necessary for web UI, which you already seen, or API servlet. This API servlet is basically running RESTfull API, and it is provided by Jersey. And these responses from RESTfull API are then serialized into JSON with using Genson. And as you can see, this API servlet is cooperating with DAO. So when you do some change, then this change is automatically reflected into DAO objects. And what this DAO objects contains, it has configuration of all modules. We call it module context, and also module context definition, which tells you what you can already configure for these modules. So let's go into backend. As you can see, here we have again a gateway service, which is a starting point of our application. But what is more important and interesting is we have module directory. Basically, this is ordinary directory in a file system. And into this directory, you place modules. Then a module class loader goes through this directory, analyze each jar file. And if this jar file contains classes which implement certain interfaces, it creates sets of informations which modules were actually found, and provide these modules information into chain manager. At the bottom, we have configuration file, and this configuration contains all configuration of modules which you will have in flows and which are stored. Configuration manager loads this configuration and update firstly DAO. So then graphical user interface can read this information, so you can see what you already have in configuration, and also send this information into chain manager. And what chain manager will do, it will combine all found modules and all configuration files and creates initialized modules. So into each module, place part of configuration which is related to this module and start some initializing process. So cache manager also holds initialized modules, but in fact these modules will not be used directly, but I will explain this later on. First, let's go through some use cases which we built. So first one was home power consumption meter. So what we have some power consumption meter which is built into electrical switchboard. We have to little bit customize this meter because it generates also signals which were fake. So we need some additional filtering. This meter produces 1000 impulses per kilowatt consumed of energy. And we count these impulses by Arduino. When Arduino counts 100 impulses, it sends information via nRF24. And this information is then received by another nRF24, which is connected into BeagleBone Black. On BeagleBone Black, it's running our IotaGate. This IotaGate will do some additional processing and send this information to external server. On external server, These information are stored, and external server also provides you RESTfull API. And out of this, you can create also fancy application, for example, mobile application. So this is how this setup looks like. So at the top, we have this power consumption meter. In the center, we have electrical switchboard. At the bottom, there is Arduino with additional circuits and nRF24. In the center, we have BeagleBone Black, and this BeagleBone Black then send information to external server and some fancy mobile application which displays, for example, your current power consumption or historical data. Since we have this first use case, we start to think how to extend this use case to even better prove suitability of IotaGate. So we create some smart temperature regulation. This time we have a sensor with actuator also. So this sensor measures temperature. Again, send this temperature wirelessly to BeagleBone Black via nRF24. Then in BeagleBone Black, it's processed, sent to external server. In the external server, it happens some additional processing, retrieving local weather information and combine this data together, and then send back feedback to BeagleBone Black, and BeagleBone Black then send feedback into actuator, and actuator open or close valve on radiator. So here we have also feedback from IoT network. Let's go into second use case, which I have already here, and luckily it's working. So I have microcontroller which is connected into IotaGate. So this is my setup. 3 kinds of sensors. This is light intensity. In the middle is temperature and pressure. This is quite accurate sensor. And here we have humidity and again temperature, but this sensor has very bad accuracy, so I use only humidity. These information are retrieved by STNucleo24, so STNucleo. And here is running some C++ code, and every 30 seconds when green LED starts shining, it retrieves information from servers, from the sensors. Yes, like this. These informations are then sent via serial port into Raspberry Pi. And on Raspberry Pi, we have running our IotaGate. And these information are then sent to external server, but can we go back to presentation? Hopefully. Okay, so this is a flow which is prepared in IotaGate to process these informations. So we have a serial input module, because as I already said, this Raspberry Pi is connected via serial cable. And this serial message is basically created simple JSON. So for our purposes, we try to transform this JSON into some internal message which can be then later on processed. For these purposes, we have JSON to message module. And then this message is divided into 2 JavaScript interpreters. These JavaScript interpreters use JavaScript Nashorn, I think. Yes, it's called Nashorn. It was introduced in Java 8. And so the bottom one removes some unnecessary data. Then additional module is timestamp module, so I add timestamp information and send it to MQTT into some private MQTT broker. At the top, I add in this JavaScript interpreter some authentication information, and this information is necessary for HTTP module. So HTTP module creates some HTTP request and send it to outer world. But what does it mean, outer world? So I create this use case to also show how we can cooperate with IBM Bluemix and Node-RED. Why we decide to use IBM Bluemix and Node-RED is because it provides you platform as a service. So we want to spend some time with configuration of systems, and therefore we try to use platform as a service, and Bluemix was a very good choice. And basically you have, I think, 3 or 4 months trial to try your own projects. So here we have 2 flows. This is everything configured in Node-RED. So in the top flow, you go to get in. So basically this is HTTP module. So from IotaGate, this information goes into get in module. Then some authentication is done to check if you have proper credentials. And then it splits into 2 parts. At the bottom, we have a modification module, which removes all information and keeps only kind of value which was measured, for example, temperature or humidity, and sent into Android push notification. So at the top, we add some additional info. So if there is not present timestamp, we add local timestamp and return this as a HTTP response. So this is top module, and also write it into EnviroData. This is our cloud-out database. So as you probably noticed, into push notifications goes only information what was measured, but not already measured values, because I think GCM doesn't hold the core informations. For retrieving core informations, we have this bottom flow. So we introduce some HTTP get data call. In get data call, you specify what kind of measured information you are interested in. So for example, temperature. Then it goes into limitation, where I prepare some NoSQL statement. I am interested only on last record which was inserted into database for this specific value kind. Then this is executed on NoSQL Cloud and database and return as a HTTP response. So for these purposes, we also have to create some mobile application. And for mobile application, I use mobile first platform. And basically, since I am not an Android developer, it took me 2 days to build such an application. So mobile application retrieves GCM notification. This is sent as a broadcast. So if you have several mobiles with this running application, then you can receive all informations in all your mobiles. And when I received, for example, temperature was measured, then I do some HTTP request, and I will request the last measured temperature. Additional reason why I don't send this information directly via GCM is because, for example, this use case just want to show last measured temperature. But later on, I can extend this application to, for example, please retrieve me last 100 measured temperatures, and then this basically not fits into GCM. So we have a more scalable application. And now I can show you also how this is actually working. Can camera come here once again? So I have to start this application. Just a second. So in a short time, we should receive notifications on mobile if everything works well. If not, never mind. Okay. Great. So basically it stops working. Okay, let's go continue in the presentation. So let's go into module architecture, because I hope this interests you the most. And let's dig into code. So this is our sequence diagram which represent classes. So we have some input driver which take care about receiving messages. And when input driver receives message, it notify all input modules which are listeners for this message. Input modules then pass work into chain manager, and chain manager will create copy of configured input module. And then this copy of input module will start running in separate process as a fork join. And from input module, when input module finish his work, it propagate message into output module. Output module again start as a separate process, and from output module it goes into output module driver. As you can see, execution of input and output modules happens in separate processes, but as a developer, you shouldn't take care about concurrency execution of your module, because IotaGate will handle this for you. But what programmer should take care of is blocking resources. So for example, when you have HTTP module and you want to listen on port 20, port 80, then you can create this module which directly call open port 80, and then that's it. But the thing is, when you once open port, then another input module which wants to open also the same port will basically fail, because this port is already blocked. So for these purposes, we introduce driver, and only driver opens these ports and notify all input modules as listeners. So basically we introduce some driver pattern, and if this pattern will be followed, then you can also handle access to blocking resources very easily. So let's go into some code. So I'd like to show you simple module architecture for serial input module for Raspberry Pi. And basically this module requires some library which allows you to access serial port, and also our module interfaces library. And let's go into source code. Okay. Can you see it? Okay. Nobody complains, so it means yes. So I'd like to create Raspberry Pi serial input module, and this module should be input module. So I implement interface input module. When we go into input module interface, this is very simple, because what you have to do is implement get message, and basically also set backtrack message, but you shouldn't. This will be handled later on. So in addition, you have to extend abstract module or extend any class which already extend abstract module, because in this abstract module we cover some life cycle stuff. So our module can be in several states, like initialized, chained, unchained, destroyed, and so on. So what is interesting is in constructor we have module context description. This is basically we described what this module can do, so what properties you can configure, and here you can configure name, baud rate, and basically we have list of allowed baud rates and some default values. Then message terminator. This is quite interesting because serial port basically just send you characters, and you have to store this character into some temporary buffer. And if you receive some message terminator character, you can tell you received whole message which you are waiting for. Therefore, we need the message terminator and also message buffer size. And basically, this message buffer size shouldn't be very big because usually these embedded devices like Arduino or Mbed has very small RAM. So if you try to build your message, for example, in Arduino, bigger than 2 kilobytes, you will basically fail because Arduino has only 2 kilobytes of RAM. So we want to also do some initializing stuff, and this is done in doInit method. Basically, this doInit method is just a hook, and if you don't want to, you can keep it empty. But probably you want to load some configuration from module context into your module. So this configuration, as I already said, is processed by configuration manager, and it serves into modules, and then doInit methods it calls. So I go into several keys and set my properties. What is also very interesting here is this line. This means I have some Raspberry Pi serial driver factory, and I ask, give me driver for this specific port with baud rate, message terminator, message buffer size, and subscribe myself into listeners. So, and what factory will do, it basically check if we already have this driver in cache, and if not, it will create a new one and register yourself as a listener. So, as I already mentioned, you can have several states in your module. One is initialized and another one is destroying. So destroy. And for destroying, you probably want to unregister yourself from listening on specific port. And when this happens, basically Raspberry Pi serial factory also check if this is last module listening on specific port, and if yes, then it call destroy on driver. But what driver will do? Driver basically serves all communication for serial ports, so it opens serial port communication link, and Pi4j allows you to create serial data listeners, and this serial data listeners is called every time you receive some character. And basically, when you don't receive character until specified timeout, then you basically get notification and serial listener will be triggered. But this basically means sometimes during receiving messages, you will be interrupted and you will not receive whole message because, for example, this specific character will be transmitted a little bit later on and timeout will run. So therefore, we put every information into buffer, and when we receive the message terminator, we can tell this message is whole, and we can then process this message into output modules, into input modules. So, and basically, Yes, of course. This is destroying of drivers, so I close serial communication, remove listeners, and call shutdown. And also, serial driver should provide you some information to write data into serial port. This is basically used by serial output module, but this is different topic. So basically, this is all what I want to tell you. And if you have any questions, please ask. If not, I can thank you for your attendance and good luck.